Tisztelettel köszöntöm az osztály tagjait és a megjelent vendégeket a mai alkalommal, amikor professzor Marlan Scully tartja meg a székfoglaló előadását. Az előadás maga is angolul lesz, és ő maga nem érti azt, amit én mondok, azért mostantól kezdve angolul fogok beszélni. It's a pleasure for us to have Professor Marlan Scully here with us, and this is my privilege to say a few introductory words about him. Marlan Scully, not a professor at that time still, he was born in Wyoming, in Casper, in 1939, and started his studies in Wyoming, first in Casper, in the college, and then at the University of Wyoming, and went to Rensselaer Polytechnic Institution. He finished his undergraduate studies there, and then went on to Yale to do his graduate studies, and there he worked together with Professor Willis Lamb, and that was a very important factor that determined his life later on. So he did his PhD there, and in '66 he got his degree. For a short while he was instructor at Yale, and then soon went on to MIT. He was first assistant professor, then was promoted very early to associate professorship, and at the age of 30, or shortly before that, he got a call from the University of Arizona to be full professor there and to build up an optics science laboratory together with Willis Lamb. That was an offer that he couldn't reject, so he went there, and from then on, roughly every 10 years, on the average, he moved somewhere else. He remained always in optics, but he moved to different places because he got different offers, and he was facing different challenges that he couldn't escape from. So first he went to Arizona, then in '80 he got an offer from New Mexico as a distinguished professorship, and then at the same time he got a position, so he had basically a joint position at New Mexico and at the Max Planck Institute for Quantum Optics. And then in early 90s, in '92, he moved to Texas A&M, where he is now as a Burgess distinguished professor. But the challenges didn't stop at that time. In the early 2003, he got an offer from Princeton to be a visiting professor first, and then he got a joint position at Princeton and had also his position at MIT. And in 2011, a new challenge, he was offered a distinguished research academician position at Baylor University in Texas. So he is now sharing his time between Texas A&M and Baylor University. At Baylor, he built up, he's building up a new laboratory, a Baylor Research and Innovation Collaborative. Now, as a long-time professor, he, of course, he had many students. He supervised more than 50 students for their PhD. I just want to mention one whom I know the best as a solid state physicist. Patrick Lee was his student. His first very important activity was, together with Willis Lamb, complete quantum theory of lasers. He worked out the complete theoretical treatment, laser photon statistics, laser line widths, all correlations in laser photon correlations. They worked out in much detail, and that was a very important work. And later on, he worked on many other things. simply cannot elaborate on all of them. I just would like to mention a few. One of them was a good qualitative description of the fluctuations in Bose-Einstein statistics. It was not treated very thoroughly, completely before, and he was the first who gave the good quantitative description. His contribution to the quantum mechanics is also fundamental. Using quantum coherence concept, he worked out the quantum eraser. We will hear about that partly during this talk. Although he is a theorist, he collaborates very closely with experimentalists, and he likes to see the realization of his ideas in actual experiments. So he was the first who invented, had the idea that if we use quantum coherence, then lasing can work even without population inversion. With coherence one can attenuate absorption, and then laser operation is possible without population inversion. So he had this idea, and with collaborators, he also has shown that experimentally that the idea really works. He is a leading expert, of course, in laser physics, quantum physics, many other things. I just would like to mention two books he has written. Laser physics is the one, quantum optics, the other one, which are standard books, standard textbooks in this field. Of course, he had hundreds of papers, over 700 scientific papers. Among the co-workers, co-authors, I would just like to mention three. Willis Lamb, the supervisor, Julian Schwinger, and Roy Glauber. They are the Nobel Prize winners with whom he worked, and of course with many others. And he has even a couple of US patents on laser physics. Well, all this activity, his research, earned him national and international recognition. So he is member of the National Academy of Sciences in the United States. He is a member of the American Academy of Arts and Sciences, member of the Academia Europa. He has earned numerous awards. Again, it would be a long list to mention all of them, so I just want to skip that, but he has earned many, many prizes. And the last thing I would like to mention is that since he has very close contacts with the Hungarian physics, especially optics community, he was elected honorary member to this Academy of Sciences. That's why he's here now, and he will give a talk, this inaugural talk, on something different than that was announced. The announcement was how to use quantum mechanics to detect anthrax. I didn't know what anthrax is. It is lépfene in Hungarian, but the talk will not be on anthrax, but on something else. So I asked you, Professor Scully, to give your talk, which is related more to Hungarian physicists. Please.
Thank you. I especially appreciate being here, especially famous place for physicists. You kindly mentioned my wonderful collaborations with Willis Lamb and Julian Schwinger, but the guy I published the paper which has the most citations to is Eugene Wigner. Good luck for me. We had many wonderful collaborations, and one night at dinner we said, well, we should write a paper on the Wigner distribution, a review article, and bring in facts other people didn't know. And Eugene said, yes, but you cannot call it the Wigner distribution if I'm a co-author. And we said, well, if we don't, nobody will know what it is about. So he agreed, but there's a footnote on the title. The title is something like the Wigner distribution yesterday, today, and tomorrow, something like that. So on Wigner distribution, there's an asterisk. It says at the bottom, one of us objects to calling this the Wigner distribution. Well, that kind of wonderful spirit is one of the reasons that I'm so happy to be here. Now, if I work this right. Let's try that. That didn't work. That didn't work. So what do you suppose I have to do to get the first view graph? Is it not these? Oh, you do that one. Oh, okay, good, good, good. So when Norbert called me and invited me to come and give a lecture, I, of course, was thinking of his wonderful institute with all of his brilliant colleagues. So I thought, oh, I would like to tell him about our most recent experiments on detecting anthrax in an unopened envelope. And it's of general interest, and it's a very important problem, especially in view of the anthrax murders in 2001 in the US. But then when I began thinking about and realized what he had said, that this was my good fortune to make a presentation to this august community, I realized, oh, that's not what they want to hear. Let me tell them of one of my hobbies. I always tell students, have two things going. One thing you just enjoy doing. Another thing that you think is important and someone else is going to support you for. So detecting anthrax, yeah, I got good support for that. Talking about quantum eraser, Maxwell Demons, well, I care about that. And in particular, all of the work in this field is really very strongly influenced by Solarz. Yeah, I'm going to need help again. I bet you there's no help for me here, though. Yep. Okay. But before I tell you about that, I remind you of something you all knew. Back in the 20s and 30s, when quantum mechanics was getting started, Hungary contributed more than its share of geniuses to the problem. And we all know names like von Neumann and so forth. So much so that the Germans called them Kugelkopf, ball-bearing heads. And in particular, Fermi, I believe, was one of the people who referred to the German scientists working on the problems of quantum mechanics one way and the Hungarian scientists another. And the Hungarian scientists that have most influenced our work in these areas of quantum optics and the foundations are, first of all, Norbert Kroll. You all know that he is a pioneer in the ultra-short pulse laser business. This is how we detect anthrax without opening the envelope. So that's why I thought about him right away. But later I came to my senses, and I didn't want to bore you. So now I bore him, but not you. Eugene Wigner, I mentioned. Oh, Norbert, I have to tell you also that Norbert Kroll is our big hero on surface physics, surface plasmons. He won the Lamb Medal for laser science, given for these types of problems, and is indeed a ball-bearing head kind of guy. Thank you for your contributions to our field. Eugene Wigner. I knew Professor Wigner from many different directions. It was my pleasure to get to know him early on. And one night I said to him, you know, I'm very interested in this question of the Wigner's friend. You know, you have an observer. This observer makes an observation, tells you of the observation, and at that point you reduce your state vector. But should I make the reduction when she tells me what she saw or when she saw it? Wigner had deep insights into this business, and that's the third part of this discussion, which was developed in large part with Schwinger and Englert. I have to confess that after I realized that the talk I had was inappropriate, I called my wonderful assistant. We used to call them secretaries, but we can't anymore. Political correctness requires I call her an assistant. And in fact, she's a theoretical physicist, So very often I'm her assistant. So I called her and I said, Kim, make me a view graph, take these two from the Prague talk, take this one from the Caltech talk, and refer to the paper that I did with Schwinger and Englert. So she did, and she comes up with this. I said, well, I called, I said, well, that's not right. You can't do that. You can't leave off Englert. She said, there wasn't enough room, and Englert isn't going to be there, isn't going to matter. So please read Schwinger et al. And I'll tell you a little bit about this as time allows, but one sure way to give a terrible talk is to talk too long. So I promise not to go beyond 45, 50 minutes, and you'll help me to know when I'm about ready to go over my time. Thank you. So Wigner, I mentioned as a great hero in the sense of foundations of quantum mechanics. I told him I wanted to write a paper on the Wigner's friend problem, and he said, well, you're all Wigner's friends, a great, wonderful human being and a great scientist. And then the other hero of mine, Solarz, actually, I never had the privilege of meeting, but 2/3 of the talk is based on Solarz's insights, the insights associated with the Maxwell Demon business. And then finally, Wigner's friend and the eraser of memory and the consequences for the foundations of physics. Now, let's move ahead. I have 3 sons. One of them is a writer. Robert Scully writes, and he's always asking questions about everything. He's also a rancher, an engineer and a writer. So one day we were talking about thermodynamics, and he said, oh, thermodynamics is too complicated a problem. It's not of interest. I like things that are philosophically simple. So I said, well, how about if I told you I can derive Carnot efficiency with a single atom engine? And he said, well, if that's true, you should write it up. So I explained it to him, and he wrote it up. And in particular, the concept of the Maxwell demon and, of course, Solarz's solution to that problem is what this is all about. His book spans the intellectual space from the Pythagorean number mystics to Maxwell's great thermodynamic insights and the way that quantum mechanics rends these questions much more transparent. May I ask you a question? How many of you know of Solarz's solution to the demon problem? Okay, fair enough. I will explain it to you. But first I have to tell you what the problem is. Here's an example. Suppose I have 2 fiber optic junctions, and suppose I send light in here at 10 photons a second, here 10 photons a second. Come to a Y junction. So out here, put them together, must be 20 photons a second, right? Right? Wrong. You can never get more out here than you have in either one of these junctions. Because if you could violate the second law of thermodynamics. And this is the spirit of his book, which is published by Wiley. But Maxwell, James Clerk Maxwell, is a hero for many reasons, not the least of which is his great human side. And he said something that I've always thought was absolutely correct, especially when teaching physics. He says, in science, it's when you take an interest in the lives of the inventors that the subject becomes endurable, and only later, when you study the ideas themselves, does it become fascinating. And in particular, today, I'd like to focus on the Carnot efficiency concept, as is explained in von Bayer's book. Carnot's theorem is the most impressive example of all of physics of the triumph of theory over practice. It establishes science as the very heart of industry and commerce. That's absolutely true. Carnot was a fascinating person. He was, as you probably all know, an officer in Napoleon's army. Go to Paris. I was pleased the first time that I happened to do that to see that there's a boulevard called Carnot Boulevard. And I thought, boy, these French really know how to treat their physicists. Wrong. It's named after his father, who was one of Napoleon's generals. And our guy has a little alley named after him somewhere. But never mind, Carnot was a very loyal officer of Napoleon's army. And as a lieutenant in artillery, he decided to study the heat engine because, as he explained it, if you take the Navy away from England, on the one hand, on the other hand, you take away the steam engine, you'll do more harm on the second go-around. Take away the basis of her commerce, and that's much more effective in subduing England than anything that you could do militarily. And in particular, the engines that they had in 1802, 1803 were very low efficiency, 1%. So Carnot thought, maybe I can build a better engine. So maybe if I use alcohol instead of coal, maybe if I do this and that, I can have a better engine developed. But it is, of course, the case that he showed the efficiency depended only on two things: the low temperature entropy sink and the high temperature energy reservoir. In Rob's book, my son's book, he offers this example of how an engine works in its simplest form. You start with two masses, you cool them, remove the ice, heat these masses. This position is locked, so the upper mass will slide upward. Then you cool the rod, and that will pull up the bottom mass. And you repeat this over and over again. And you see then the essence, the simplicity of this device is that it involves a high temperature and a low temperature. And in particular then, as Solarz began looking at these problems, it became clear to him that all you needed was one atom. And he could explain this business of Carnot efficiency on the one hand and the Maxwell Demon on the other. So you'll forgive me if I skip around a little bit on these view graphs because I didn't get to proofread the talk, but here's the deal. If all that's involved is hot and cold, then that's very interesting, because why don't we just take the ambient atmosphere and use that as a source of energy? And furthermore, with this infinite source of energy, solve all the world's energy problems. And Carnot, as you know, and as we'll go back to in a moment, showed that that's not possible. You can't run an engine without two temperatures, the hot and the cold. Okay, we teach this in our freshman physics course. But Maxwell said, yes, but what if I include in our discussion the concept of a friendly demon? And what if this intelligent device is such that he only lets hot atoms go through the door going this way, and if it's a cold atom that comes up here, he keeps it on this side. So after a while, he has hot and cold, and this way he could then run an engine. And in particular, then, we come back to Solarz's ideas, and I only show this because it shows how even the best of us can go wrong in some of these ideas. Walter Thirring, famous Austrian physicist, the Lenz-Thirring effect in general relativity. His son is a famous theoretical physicist and a great scientist. He says something very interesting. He talks about Solarz arguments, and by the way, I'll come back to Solarz in a moment, but he says the thermodynamic limit is not valid for one atom. Very interesting and very wrong. Let's go forward a minute and look at what Solarz engine is all about. Let's go one or two more. Where's Solarz? There he is. Here's Solarz's idea. He says, let's have a configuration with two pistons. And let's put one atom in here and have a movable partition. So if at time t equals 0, I slide the partition in place and my atom is down here, then it's isolated from the top piston. So now we have a little indicator that says B for bottom. Atom is in the bottom. So we know go to the top piston and push it down at no cost to the customer. No energy expended because the atom is isolated from that piston. Then we pull the diaphragm out, the movable partition, and following Solarz, we apply heat to the walls. Now the atom will bounce up, hit the piston, recoil, transfer some energy and momentum to the piston, but it will then collide with the walls and come back to equilibrium at this temperature. And now we let that happen until we go back to the original spacing, and we've now done work on this piston by virtue of the many isothermal collisions. And at that point, we have to erase the B. We have to reset our device so that it looks like the original device. So we reset the B. Now, Turing was offering the notion that the single atom issue is the big problem. But Solarz said essentially correctly, no, it's information. It takes energy, entropy and therefore energy, to change this B back to a neutral register. And so that was Solarz and his very insightful point of view. Let's go back now. Back. So the Maxwell Demon business is a issue that Solarz made understandable and very specific, okay? Nothing complicated or confusing about consciousness and so on. But back to my original statement and to Solarz's utilization of a single atom. So when I first arrived at Princeton, they asked me what I wanted to teach, and so I said quantum chemistry, right? Because that sounded like the right thing to teach. And they said, oh, fine, but you know what we really need help with is thermodynamics. So I thought, well, that would be fun. I haven't taught thermodynamics for many years, so I started off by teaching that I could operate an engine with one atom. And I was following Solarz really here. And so I start with the piston at top dead center, hot atom. I let the atom do work on the piston isothermally. So you remember the entropy, temperature, entropy diagram. So this is isothermal work. Then I do adiabatic work, take the heat away, let it continue to, the atom continue to push on the piston, stop at the low temperature that the atom has achieved, and now begin to compress, do waste work, but this time put the walls in contact with a lower temperature, T cold. Over here I should have said T hot, there it is, T hot. And I do this compression until I reach the original configuration. Well, the amount of work that I'm able to gain from this first expansion stroke is just kT log 2. I've got twice the volume, the entropy is doubled, and so without doing very much algebra, I can convince myself that the work out, the useful work equal to the heat in, is kT log 2. The waste work is the same thing, except now I'm putting work onto the piston, and the entropy sink, the river, the cold river, is keeping things at the temperature T cold. Again, I'm going from here to half the volume, log 2 comes in. So the ratio of these work out minus work in over work out, this is the good work, the high temperature work, is always log 2, and the k's cancel, Boltzmann's constant of log 2 cancel, and I have 1 minus Tc over Th. That's the Carnot result, which Carnot obtained in 1802 or 3. Point being that we do all this without thinking about conservation of energy, and certainly Carnot didn't have the first law of thermodynamics even, but due to his ability to pick the essence of the problem out, we see that this important factor comes to us. So no matter what the engine is, and here's where Carnot really drove the physics home, whether it's a lawnmower or a nuclear reactor or a coal-burning locomotive, the efficiency is always determined by this simple expression. Now, I'd like to step aside for a second and tell you something that I find very interesting and something that's really taking a lot of people into the area of quantum thermodynamics today. And that's that if I look at a maser or a laser, I can think of this device as operating between two temperatures. One temperature where I'm pumping the atoms to an excited state, a lower temperature in which I'm effectively cooling the atomic lasing medium. And as I'll show you on the next view graph, what we find as the efficiency for this device, work out governed by the difference between the in and the output energy, is again Carnot. Again Carnot. Now let's elaborate on that. Here's how you think about it. And this was first pointed out by Schultz-Dubois and another Swiss physicist whose name I'm blocking, sorry, in Lucerne. And these guys made the following insightful observation. They said, how do you make a population inversion? Well, start with most of the atoms, say 80% here and 20% here, and put on hot radiation, incoherent hot light, as governed by the Planck distribution. What that will do is bring the number of atoms in the C state and the number of atoms in the A state to be equal. So I've got now 40% of the atoms here and 40% there, or some number, but I typically don't have inversion yet. I've chosen my numbers poorly, but you'll bear with me for a minute. What if I did this? 50% here and 50% there. Ah, good. Now I can do something in which I equilibrate 25 here, 25 here. Oh, but I still got 50 there. So now what I do is I apply cold light. And the cold light then changes the populations into a configuration such that I can have inversion. And that is to say that the ratio of the population in the A to the B states can be written, let's just divide and multiply by the population in the ground state, and then let's put in Boltzmann factors for the A over C ratio, top to bottom. So that's the energy of the pump photon divided by kT hot. Then we've got the other ratio of NC to NB, and that, modulo a minus sign, is the ratio of this BC. So I've now got the energy of the maser photon subtracting off most of the pump photons. So this difference is just this difference. So if I want this to be at threshold, this equals 1. So put that equal to 0, and now just solve a couple of manipulations, high school algebra, and I end up with this quantum efficiency of the maser is equal to Carnot efficiency. So I love this because it's a completely different example of how we can get the Carnot efficiency and not the typical example that goes with the isothermal adiabatic and then low temperature isothermal adiabatic. So this is the usual textbook argument. Here's a new argument emphasizing that masers and lasers and thermodynamics are really quite closely related. I'm pleased to remember that we got quantum mechanics from Bohr, who was studying the entropy of thermal light. And then Einstein, 5 years later, used Bohr's ideas, studying again the entropy of light to come to the concept of the quantum, not the photoelectric effect, as you've pointed out in your papers. Now, let's go on. So what have we done? So far, we've convinced ourselves that the Carnot efficiency is something which is interesting and perhaps deep, has some connections with thermodynamics and quantum mechanics, and that a la Solarz, this little bit of information, the register, which told us whether we're on the top or the bottom, is essential to understand. Well, we start our now summary of what the greats said about this business. And Maxwell started off by talking about using a being who has intelligence, and therefore without the expenditure of work, it can create two reservoirs, one hot and one cold. And if you can do that, you can have perpetual mobile of the second kind. But you cannot. And Solarz gave us this example of how to make a Maxwell demon, and he opted that it's information that costs. He's not far wrong, but not quite in keeping with the modern point of view. And Brillouin offers the thought that perhaps the demon can't see the molecules after a while because of black body radiation. That's completely, I think, off the mark. Wigner, Norbert Wigner, MIT physicist, really is much closer to the fact. He says in the long run, the demon itself is subject to random perturbations. And after a while, he ceases to act as a Maxwell demon. Well, go back to Solarz. After one cycle, you don't have a Maxwell demon anymore. So if I go to a more complicated kind of sorting device, you can see that there's a deep sense in which Wigner has it right. But let's go on. Now another statement of Solarz, which I agree with completely. He says, Solarz has the idea of trading entropy with knowledge. That's not so far-fetched. S equals K log complex, right? So that we know information and state of mind. What we know about the system is what determines the entropy. This seemingly crazy idea led to the fruitful Shannon information theory point of view. Now comes something closer to the modern perspective. Bennett, he's a revered figure in the field of quantum information, quantum computing physics, says that Solarz engine does not violate the second law because erasing the information during the last step is thermodynamically costly. One needs k log 2 entropy per bit of information erased, right? But then he brings it into sharp focus. He says, this is confusing. We pay to have newspapers delivered, not taken away. Good point. Now, having used up most of my time on the first of 3 talks, I now go to the resolution of this Maxwell Demon problem, this time thinking specifically about one kind of engine, namely the maser engine. But here, the great statistical mechanician Terhar, from whom I had the good fortune to learn thermodynamics, says that the entropy introduced in information theory is not a thermodynamic quantity. And this is rather the source of much of the confusion. Well, I think we'll come to agree with Terhar, but on the other hand, probably agree also with Wigner and with Bennett. So just to conclude this business of what do people say, you'll find Fizerev letter articles which argue that there's no process of erasing or throwing away information necessary. And there are others who show this business is problematic. And on the weekend, when I am working on the problem I want to work on, I was able to show that I never need to introduce information or entropy to understand the Solarz problem. And the essence of that business is focusing on a simple model and remembering that in thermodynamics, like nowhere else in physics, the devil is in the details. One must be very careful at each point to think through the physics simply and effectively. So suppose now I have a wave packet. Classical physics suffices. I have a probability packet. I have atoms in the up and down, spin up, spin down configuration equally. That is to say, my spin 1/2 system is at infinite temperature. I pass into a Stern-Gerlach magnet, and I kick the up spins this way and the down spins that way. Nobody can stop me from that. Then, following Towns and coworkers, we pass this inverted spin state through a microwave cavity. And we stimulate the atom to the ground state, emitting a quantum of maser photon energy. If, on the other hand, I go on the down path, then I come here, and I just now need to put these beams back together and come over here. I got to go through a whole round where I heat them up again. I shouldn't have that upstairs. That should be downstairs. See, everything's downstairs. I put them together, so 0 temperature, go through the whole round, and then I want to rebuild the original condition. Not trivial. Try it. Well, how about this? What if I just take 2 wave packets and I combine them at this Y junction? Wouldn't that work? I put them like that. No. No. Because if you try, what you find is that there's a kind of ricocheting, a bouncing, so that my atom, my one atom system, or one spin system, is not going to emerge moving in the forward direction, but going off that way and that way. No go, that doesn't work. Let's try something else. Let's try a beam splitter, okay? So first of all, you remember from your optics course that if I come in with a photon or a packet of electromagnetic energy, put it through a beam splitter, put it on a beam combiner, then a la the Fresnel laws, I can show that this packet gets divided in half and is put back together over here. Oh, that's good news. But the bad news is that it doesn't work if I have a thermal. Where's the rest of my picture? There it is. It doesn't work. What doesn't work? It doesn't work that I can get these two beams combined if I have thermal light, incoherent light coming in. I have to have one pulse only with one specific phase. And when I go through the whole realm, I'm going to mix these phases. So that's not going to work. Looks like we've got troubles. But here's the way out, a particularly simple configuration. Suppose we put a delay line in the lower path. No problem there. Then at some time, after we've gone through the maser cavity, all the spins are in the ground state. The first spin is here, and the second spin will be displaced because of the delay. So I can now go to a rotating mirror. That's on the next part of the view graph. I go to a rotating mirror, and I have it phased such that when these spins come down, they hit a vacant spot, and I slip through the system. But when these spins come up, they're behind the first, and they hit a mirror. So now I'm in line between the up and the down legs, and now I go through again with a timed rotating mirror. I go into a piston configuration, and you see what I'm going to want to do now. I go into the piston, I slide in a diaphragm, and so no matter whether the spin is here or there, it is either one or the other, it's not both. But if it's like this, I've trapped my atom properly, and if it's like this, so that if I went on the top or the bottom path, in both cases, I've trapped the atom. But now I have to do isothermal compression. Hallelujah. Now I see where the energy is involved, the waste work, as we say, because now I put everything together, and sure enough, I can get energy out on every pass, but I have to do isothermal work here. But please to note, by the way, there's only one temperature in the problem, and that's the temperature of the whole round. So that when I go back through and calculate now the total work, I get essentially kT over 2. kT is about equal to h bar omega. So that's a good approximation. So half the time I get the photon out of energy h omega equals kT. On the other hand, over here, I have compression, which goes like kT log 2, log 2.6. So I'm doing more compression work than I'm enjoying from the engine work. On the other hand, this is low entropy radiation, and I can do things with that. I can drive machines. I have a real working engine that takes in high temperature, incoherent energy and puts out low entropy, coherent work. So that's the conclusion to this particular quantum mechanical Stern-Gerlach device. We've shown that a Stern-Gerlach apparatus can be a realistic Maxwell Demon and presented a quantum heat engine based on this. Our engine sheds new light on the Demon paradox as it provides a resolution without need of entropy arguments. So entropy arguments are useful, and they're designed to save us calculation. but I can always do these problems. I can always do the calculation step by step and find the amount of energy involved. So we have, in this sense, a good rendition of the Solarz engine and a very simple example of how the waste work, the low temperature entropy sink kind of work, must be put into the problem. Now, as I should ask, how much time do I have before I've used up? How much?
10 minutes.
I have 10 minutes. Great, I can give 2 more talks. Let's go on to the quantum eraser. But you know, I didn't tell about Teller. So Kroll is my item. Wigner is my hero and helped me to get a paper published that I could put in my resume. Teller, not so much. Lasing without inversion. We were making lasers work without population inversion, and we succeeded. We had it experimentally. So Teller was at the conference, and he gave the first talk, and I had the second plenary talk. So here's Edward Teller. So I feel good about that, right? So he gives his talk, which, by the way, was how the Jahn-Teller effect explains superconductivity. Interesting. We've all heard that talk. Good talk. So he sits down in the front row, leans on his cane, waiting for this next guy to get over so he can leave, right? And he hears, lasing without inversion. And Teller never tolerated fools. So he looked up, and he saw what I was saying, and it made him angry. So he got up, and you remember he had only 1 foot because of his accident as a student, and he stomped out of the lecture room, and that, of course, was the end of my little ego boost for having Teller in the audience. But that night, he was wandering around by himself at the hotel, and so we asked him if he would join us for dinner. So, you know, any port in a storm, so he said, okay. So we got him to sit down, and I showed him step by step what we were doing. And then he understood it, and he said, okay, oh, this is great. So he was kind of a converted friend, but also a great genius, as I learned to my dismay later in life. I did get to teach quantum chemistry at Princeton, and so I wanted to teach something a little different. So what are you going to do? You start with the hydrogen molecule, and you're going to do ordinary Heitler-London. Now, let's not do that. Let's go back to the idea of using H2+, 2 center orbitals, and let's solve for the molecular binding energy of hydrogen that way. Well, it takes a lot of mathematics. Confluent hypergeometric functions were part of what I learned in graduate school, and so I thought that would be a good thing to do, and nobody else had done it. In fact, I asked all my friends, do you know? Nobody knew, even the quantum chemist. So I worked it out, wrote up a paper, published it, and then you get the hate mail, right? They tell you which Hungarian physicist did it first, and it was Teller, 1930-something, in his thesis. So I was only about 70 years late. But, of course, I was always a great admirer of Teller's intellect. Now, he should have been the head of the theory division at Los Alamos. But Beta, who made the choice, realized that this nuclear theory division wouldn't be a happy division with Teller as the director, so he chose Weisskopf. And Teller goes into Weisskopf's office and complains, and Weisskopf said, well, probably they think I would be nicer to work for than you. And Teller didn't agree, so he left and started Livermore. But what a great intellect and a great physicist from many points of view. Coming back now to Wigner. I should tell you, I steal lectures from any of my friends and some of the people who aren't my friends, but I always try to give him credit. So this is a lecture that Zuberi gave, and I took it from him. He tells about quantum eraser. And here we come to the Wigner friend business. If, in fact, we have information of the type that's indicated here, two-slit information, right? If we set up an experiment so we can tell which slit the photons or the atoms or whatever go through, then we destroy the interference pattern. So I published a paper on this business many years ago, and Newsweek got wind of it, and they wrote it up in a very nice, simple discussion. They say, well, we've long known that when particles of light or atoms go through two slits, we get an interference pattern, bright, dark. But now we find out later that if a detector or a Wigner friend monitors which slit the photon passes through, the photons no longer form the interference pattern. Somehow knowledge of the paths of the photons through the slits affects their behavior. It's as if they know they're being watched. Okay, so now I ask, when do these fringes go away? When Wigner's friend makes the observation, or when Wigner's friend tells me, sitting over here at the screen, what he saw? Well, then you can say, yes, but what if we erase the information locked in this detector or in Wigner's mind? Do we get the stripes back? And we find that losing information of the photon's path, even after the photons have landed on the screen, we get stripes back. And Newsweek opposite, that it's as if the past has changed. No wonder Einstein was confused. Well, then we go on with several different ways of achieving this, and we did achieve it experimentally. But along comes a very bright young physicist from someplace in India, and he's obviously a New Yorker from the way he writes, but he tells that this business of eraser can only happen if we erase before the atoms or the photons make a mark on the screen. So I won't go through the resolution. We argued with him for a couple of years, and finally, I think it was more Englert than anyone else, but I like my argument better, convinced him that we were right and that you could make eraser even after the events were in fact observed on the screen. So Marhoff writes, and I don't know if you can read it, I'll try. I can't read it there. But what he says is, I was wrong, I apologize. But it was the referee who made me say this. So we had a lot of fun with these things. And the bottom line is that now quantum erasure is part of the literature, and it appears on the cover of my favorite quantum mechanics book. So my voice is gone. So is my time. Thank you.
Thank you, Marlan, for this very interesting talk. And it's now my privilege to hand over to you the diploma that certifies that you are honorary member of the Hungarian Academy of Sciences. And I congratulate you.
Thank you.
Thank you very much.
I have to prove to Norbert that I'm an experimentalist and I can get this out of here. Oh, that's great. What a great honor.
Thank you very much.